So, we are discussing about the steepest descent method. In steepest descent method, what we have seen is that solving Ax is equal to b for an let us do Ax is equal to b is equivalent to find out j minima with j is equal to x transpose Ax minus x transpose b, and provided A is if and only if A is symmetric positive definite matrix. So, here in solving a matrix equation is substituted by finding out minima of a particular functional. Now, why we are doing this? Because we have discussed that the direct iterative methods like Gauss-Seidel or Jacobi has certain limitations. We want to come out of those methods and explore the other ways of iteratively solving x is equal to b. So, what we started here is that solving x is equal to b is same as if A is a SPD symmetric positive definite matrix, solving x is equal to b is same as finding minima of the functional Jx is equal to x transpose Ax minus x transpose b. Now, we are with the question that how to find out minima of a function. So, what we have observed that if we take any arbitrary value of the primary variable x, the function and define the function Jx, Jx reduces fastest at that particular location in the direction of minus grad j. So, we will move along minus grad j and try to find out what is the minima of j. And what we have done is that we have drawn the isocontour of j, and a normal to that is the direction of minus grad j, started moving along that, and this line j minima is somewhere apart from this line. If only if the isocontour is a circle, the any normal would have taken me to the center. Now, it will not take me to the minimal value, not to the minima. So, it will miss the minima. So, we will go up to certain distance and then we will draw the j isocontour again. This is another isocontour and go drop a minus grad j. So, this is again a minus grad j nu at this particular location and move along that. In a way, we will keep on changing the such directions and finally approach the minima of j. So, we will look into the detail of this method now. So, we started with one particular value, one particular j isocontour, and there is a j minima moved along along the minus grad j, reached somewhere, and then we got the new minus grad j and move along that, and then again we reached another isocontour and then move along minus grad j. So, somewhere we will reach it. The question is that how far should we move in one particular direction? What is the amount that we should move here? What is the amount that we should move here for fastest convergence or for reaching the j minima fastest way? See, if I move out of this up to here, this is tangential, right? After this j is actually increasing. Here minus grad j is 0, like this line is parallel to the j isocontour. So, if I move along this particular line, j is not increasing here. Now, j will keep on increasing. So, we can go to a minima locally along one particular such direction and then j will keep on increasing. So, if we move along this, we will never reach j minima. This is the probably nearest point to j minima. Again we go here and somewhere we have to stop, otherwise we will miss this line, we will go away, again we will come back to, if we keep on going this, if we keep on going this, again I will come back to the old j value. So, I cannot do that. Somewhere I have to stop and make a new search, find out the new minus gradient j and move in that direction. And the main idea of the steepest descent method is that start at some point x0, find the direction of the steepest descent at this value at that point of steepest descent of Jx, which is minus grad j there, and move along that direction as long as Jx reduces. And at that point when j stop reducing, so along this line move in a direction where j is reducing. When j will stop reducing, you change the such direction. At that point when j is not reducing any further, find the new steepest descent direction and repeat the process. That means, again calculate minus grad j and move along that direction. Again see where how long it is reducing, when j will stop reducing, because anyway j is bound to reduce if minus grad j, if grad j is non-zero, along minus grad j, j will reduce. See how long minus grad j is reducing. Why j will not keep on reducing along minus grad j? Now if I look here, say j, there is some value jx, something jx is equal to f of x. Now if I, and I calculated minus grad j here, when I came here, the isocontour of j is jx is a different function, jx is equal to g of x, or rather instead of jx is f as a particular constant value, jx is equal to say g. Now grad g is not same here. So if I move along this line, this is perpendicular, this is the direction which is anyway perpendicular to this particular isocontour also, and this is the direction in which j is reducing fastest. When I came here, j, when I just move away from this line, minus grad j at that point is different. So j is not reducing fastest in that line anymore, only in this point j was reducing fastest. Now j is the reduction, rate of reduction of j will slow down, because minus grad j is different. If I draw a contour here, another isocontour here, that will probably have a different minus grad j direction. So the drop is in a different direction. So it is not the direction where j is reducing faster anymore. However, we will still keep on continuing that. We will come here where j is not reducing any further. Why? Because grad j is tangential to this grad j, this particular value of grad j evaluated here is tangential to this isocontour. So if we change j little bit, if we move little bit along grad j, j will not change, j is constant. If we come out of it that, then j, if we move further, j is increasing. So I have to stop here, and now I will evaluate grad j at this point, because here j is not reducing any further, and make a new search. And geometrically it is well explainable that you move along one particular direction, see that this direction vector is getting tangential to a new isocontour, you stop here, take another turn. But how to find out it mathematically? So the question is how long the value of j will reduce if we move along minus grad j? Where should we stop? How long will this value reduce? The same question I have started with an x 0. How long the value of j x will reduce if we move along minus grad j evaluated at x 0? This I am moving along this minus grad j, however, this is evaluated at x 0. So if I come to any other contour, if I think of any other contour, minus grad j is evaluated here in a different way. So it is not probably the way where it is reducing in the fastest way, but still it is reducing, but here it is not reducing any further. So you have to find out how long value of j x will reduce. Then they are up to then, I started with one particular value of j, I am trying to reach j minima, and this is an iterative method. I started with some guess value of x where there is some value of j. I took a method which will take me to the, I am trying to get a method which will take me to the minimum value of j. Why I am trying to take a method which will take me to minimum value of j? Because if A is symmetric positive definite matrix, then the way I define j, j minima is the solution of x is equal to b. So I am trying to reach j minima starting from any arbitrary value of j. I will see the value of j is reducing, the value of j will keep on reducing till I reach j minima ideally. If I can go in any direction, I should reach, after I reach j minima, value will increase. If value of j is increasing, I will never reach j minima. I am going in a I started with one particular value of j, I am moving in some direction. If value of j is increasing, I am not reaching minima, I am going away from the minima. So I iteratively I will start with one particular value of j, move along one direction, work till value of j is reducing. If I reach minima, I reach the least value. I will see if value of j is reducing, I probably have not reached minima, but it stopped reducing. So, if I still move along that particular direction, I will never reach minima. So, I have to stop that point and then check the search direction. So, how long we will move along grad j? Till the value of j is reducing along that direction. How long value of j will reduce if we move along grad j? It will not reduce forever, because after a particular step it will keep on increasing, because this j line is probably not, grad j line is probably not taking me to the minima. A functional does not change its value along its tangent. So, when I will go along this direction, as soon as the grad j become tangential to one particular isocontour of j, the value of j will further not reduce. A functional does not change along the tangential direction. So, if value of j reduces till, the value of j will reduce till minus grad j x 0 is tangential to j x evaluated at a different level. So, x is a multivariable function. I started with one particular value of x. I can think of a 2D function where it is an ellipse, there are elliptical contours, x 0 square plus y 0 square is equal to constant, f of x is equal to x square plus y square. So, I started with a 1 x 0 y 0 and evaluated grad j there. I moved along that particular line. Now, reached a point where this line has become isocontour to another x square plus y square is equal to b, or not a, x square. I started with x square plus y square is equal to a contour, moved along grad x. Now, I reached another line where x square plus y square is equal to say c square, another different line, and this line is now tangential. This contour is now tangential to grad j. So, I will stop here and change the direction. So, the value of j x reduces till minus grad j x 0, which is evaluated here. J will reduce till this is tangential to this particular contour. Then we need to change the descent direction. So, descent means we are coming down to the minimal value. So, I will find out the new grad j here, which is the new value, say this is x 1. So, this is minus grad j x 1. I will find out the new value here and move along it. And again I will, how far should I move, when I will see that this is again tangential to another particular isocontour, maybe there is another isocontour like this and this line is tangential to that. I will come here and then I will evaluate again minus grad j and move in that direction, and that is how I will approach it. So, the method is pictorially like this. You start with one particular x 0, move along a direction, see it is being tangential to the functional here, then you change the direction, move along this, find x 2, and so this is like minus j x 0, this is like minus minus gradient of j x 1, this direction is minus gradient of j x 2. You come to x 3 and change the direction, and so on, you approach the minimum value. This is the minima. So, starting from any arbitrary value, this will take us to the minimal value. I am trying to explain this geometrically, and geometric explanation is only restricted to R2, to 2 variable functions. Like all these curves are for 2D curves, 2 variable functions. We can extend it maximum to the third R3, but this geometric concept is applicable for higher order and Rn things. However, once we finish this discussion and propose the final algorithm from steepest descent, we should check that algorithm wise that converge, or geometrically we can see that starting from any x 0 y 0 it will take me to the minima. In Rn the algorithm also should converge, that is starting from any x 0 value it should converge to the right solution and we should approach the J minima. We will check it once we are done with this discussion. How to measure the distance that we should move in one particular direction. So, this distance x 0 to x 1, x 1 to x 2, how to measure this distance, that we should move along one particular of minus grad j. A move will be terminated, the idea is that a move will be terminated once the search direction is tangential to the functional isocontour. So, we will start with a search, we will start search with a particular search direction which is based on minus grad j x 0. Based on the value of x 0, the search direction, based on the value of x 0, this search direction has been taken. This direction, this search direction is tangential to one particular isocontour, then the move is terminated. So, when should again we will stop, which isocontour, because we can have infinite number of isocontours there. We should stop in that particular isocontour, after which this value j will keep on increasing, or this is the isocontour at which we are stopping. That means, where this such direction is tangential, this will go with the such direction, check where this direction is being tangential to one particular isocontour, there we will stop. After that j will keep on increasing. So, I have to start with a such direction and check when this such direction is being, such direction is will give me some grad j x 0. When this grad j x 0 is being tangential to one j x, that is grad j x 0 dot grad j x will be 0, new j x will be 0. The new search direction and old search directions are perpendicular to each other in a sense. Assume and also another factor is that if we go along this particular line, locally j is, so if I smallest, I will not say minima, or if I draw say j versus x along this line, so this is x 0 and this is x 1. I will see j is locally local minima is along this line. At this point j is locally minima, because here j is not increasing any further, then j will keep on increasing. So, I will get a local minima on that particular line. So, now I can probably search it in that idea also, that I will go along one particular line and see when j is minimum along that line. Instead of finding out a global minima, I will find out local minima along one particular search direction. Where j is minimal, I will change my search direction. Why j is minimal there? Because j is being like grad j is the direction in which j is changing. Grad j is tangential to the isocontour. That means, over that isocontour j is not changing, along the isocontour j is fixed. So, at that point grad j is not giving us any change of j, because it is tangential to the isocontour of j. So, this is the local minima of j 2. So, I have to find out the local minima of a function along a particular line. So, we will first express the function along a particular line, how the function changes along the particular line. Assume a point x 0 which belongs to a real number coordinate of or dimension in Rn, and a vector v on that same space Rn, and then the equation x is equal to x 0 plus alpha v, alpha is a real number, represents a line going through the point x 0 and in the direction of x 0 plus in the direction of v. So, this is actually very straightforward, I have a point x0 and a direction vector v. Any point here, any point x here can be represented x0 plus alpha v, and this distance is alpha in that sense. Now, the problem is find the minimum of the functional of j on that line. That is that at this point j will also be, I will get j of x0 plus alpha v, and this v here is gradient of minus j. So, I have to find out along this line where j of x0 plus alpha v is minimum. Now, if v is fixed, given the point x0, v is equal to minus gradient of j at x0, or let me write it down somewhere else. So, we got v is equal to minus gradient of j x0, that is the direction along which we are doing the search. This is the direction v, direction vector v. So, I started from here, v is fixed, v is a particular direction which is fixed. I started from here moving along v, j is evaluated as j of x0 plus alpha v. X0 is fixed because that tells me what is the direction from which I have started. V is fixed. So, the only variable is alpha. So, depending on the value of alpha, I should get j minimum somewhere in this line. The local j minima will be where for one particular alpha, where del j del alpha is equal to 0. That is, find the minima of the function f of alpha j, which is j of x0 plus alpha v, as x0 and v are constant for our real variable alpha. Depending on the depending on the value of alpha, this will have a minima. This becomes only a function of alpha now. So, f alpha is equal to j of x0 plus alpha v is equal to half of x0 plus jx. If we remember the old functional term, j is equal to x transpose Ax minus x transpose b, and A is symmetric positive definite SPD matrix. So, j of x0 plus alpha v is half of x0 plus alpha v transpose x0 plus alpha v, x0 plus alpha v transpose into A into x0 plus alpha v minus x0 plus alpha v transpose into b, which is half of x0 transpose Ax0 plus 2 alpha v transpose Ax0 plus alpha square v transpose alpha v. So, if we break it down, we will get this expression minus x0 transpose b minus alpha v transpose b. Now, we need to find out an alpha for which this f is minimum. So, v is fixed, A is fixed, b is fixed, x0 fixed, alpha is only a function of f, where f is minimum, d alpha df d alpha is equal to 0. So, we got d alpha df alpha alpha is equal to 0, or if we go back to the old form, we take a derivative with respect to alpha, which will, this is 0, this will be 2 v transpose Ax0, 2 and half will cancel out. So, v transpose Ax0, and this will be 2 alpha, 2 and half will cancel out, alpha v transpose Av, and this is v transpose minus v transpose b. So, this will d alpha will give me v transpose Ax0 plus alpha v transpose v minus v transpose b is equal to 0. So, alpha is equal to v transpose b minus Ax0 by v transpose Av. This carries out here. Therefore, this is the distance, this is the amount alpha that we should go alpha v, we should go alpha v along one particular direction till we get the local minima from which the search direction should be changed. Or I will start with one particular value x 0 and go along alpha v is equal to alpha into minus grad j evaluated at x 0, alpha into, sorry, this is alpha into this. So, I will go alpha into gradient of j x 0 in this particular direction, and here I will get j alpha is minima. So, I should change the direction. Then again I will calculate what is the gradient of j here, and based on which I will calculate what should be the alpha. So, as v is gradient of j, this can be also written as gradient of j into b minus a x 0 by gradient of j transpose a into gradient of j, or rather this is at evaluated at x 0, this is evaluated at x 0, this is evaluated at x 0. So, again when I will come here, I will reevaluate the gradient of j and reevaluate the alpha and go along that direction. I should reach the minima. Again, because we are saying that j has a local minima here, it is also important to show that d2f d alpha square is equal to 0 if f has a local minima. This is the global minima and this is the local minima along that particular line. And then we can see that if we find d2f d alpha square, this will be v transpose a v. We differentiate it. So, this is 0, this is v transpose a v and this is 0, v transpose a v, and this is always greater than 0 as a is positive definite. We started with a is a positive definite matrix. So, we will always get at this point f is minimal. This is always a minima of f. So, now we know the distance that we should move to reach the j minima, and then in next session we will see how can we implement in a code, or how can we finally write an algorithm which will solve b minus a x, considering it to be a problem of finding j minima. Thank you.